Okay, let us continue with the response surface for the second part. Okay, so for the first part, I have mentioned it to you that the response surface were related to the regression model, where your regression model were given by the following one, where you have a first order model and you have a second order model, where they involve the quadratic terms. Okay, so before you go for the second order model, under the first order model with the iteration, you can observe it that this is some sort of the response surface, and then this one is the contour. So we are looking for all the response surface or the regression model so that we can locate the maximum or the optimal solution. Okay. So under the ANOVA of the two power factorial design, we can write down the equation because under the two power factorial design, we can get out all the, if under this case is for the two factor, then we can estimate the effect for the A, the effect for the B, and the effect for the AB. So therefore, we can calculate out those of the sum of square for the A, B, and the sum of square for the AB. Then we can test the ANOVA whether which factors they are significant. Okay. So beside that, we also can be using the effects to form the regression model. Okay. With the, if our regression model involve the factor of the main factor of the A and the main factor of B, and as well as the iteration, then we can use the effects to calculate it out. So how we want to do it is based on the effects here, then we can calculate out the regression model. Okay, of course you can use the equation in your chapter number 10 for the regression modeling to calculate the beta naught, beta 1, and the beta 2. But under the here, you can be using it by converting the x here is a coded variable where you already denoted it as a -1 and +1. Okay, then the beta naught, beta 1, and beta 2 can be obtained. Just the effect itself, just the effects for the beta naught hat, it's just the average value of all the observation. Where else the XA is the effects over 2, the XB or the X2 will be effect divided by 2. Okay, so this one is the involve only the first order model without the iteration. You have another one is with the iteration. With the iteration, also the iteration can be obtained by the effects divided by 2. So all these things is what you have studied before, the effects. So therefore, we not necessarily need to use the following formula to obtain the parameter estimates for the regression models. Okay, so this one is what I have discussed with you all. Okay, about the regression models. And then in the last part of the last week session, we have discussed about how we want to test whether the quadratic term will be important or not the important. So how we want to check whether this component is important to be put in the model or not. We will need to have an extra point to check whether this point is necessary or no. Okay, that one is called the center point. So the center point we denoted as a 0, where the coded variable for the lower level and the upper level we denoted as a -1 and +1. So the center point will be 0. Therefore, you can see that if you have a low level, you have a low level, you have high level, you have low level, you have a high level for the x1 and the x2, then the center point will be the 0. Okay. So to test whether the sum of the quadratic term is important or not, then I have show you how to do it. I have shown you the formula how it derive it. Okay. This one I don't want to repeat it anymore. Okay. So these are the things I have shown it to you. We can test the hypothesis whether the quadratic term will be necessary or no. Okay. So after this thing, at the last slide of the here in the previous section here, I also have tell you these are the equation where we want to form for the second order model. where the second order model will involve the quadratic terms. So if you observe this equation, you consist of the first point, the first unknown, the second, third, and fourth until the fifth unknown. Okay, you have a number 6 is a beta naught, beta 1, beta 2, beta 3, beta 1, beta 2. So altogether is 1, 2, 3, 4, 5, 6. You have a 6 unknown parameter. However, when you run your experiment, only you have a number of factorial point is 4, and then the number of center point is a number of center point you can have depends on how many center point you have. Okay, so maybe you only run for 1, but altogether you have only 1, 2, 3, 4, 5 different sets of them. So therefore, this one is may not enough for you to estimate for the beta 1 and beta 2. So therefore, you need to run the additional point. It's called the actual run. Okay, if you want to estimate for the beta 1 and beta beta 2. Okay, so these are the thing is what I have mentioned to you. So this type of the design is called the central composite design. Okay, where they involve the second order response. Okay, so this one is what we have discussed in the previous session. Okay, so now today we will continue with the response surface. Okay, so under the response surface, we are looking for the locate for the maximum and the minimum points you have. Okay, so how are we going to locate for the maximum or the minimum? So we call as the method of the signal action. Okay, so the objective of the experimenter is to move rapidly to the general vicinity of the optimum. Okay, so we use a very simple ideas, okay, or the efficient experimental procedure. So when we are removed from the optimal, we usually assume that the first order model is adequate approximation to the true surface in the small region of the X. Okay. So this one is a diagram where I show it to you before. You have a following one. In the following area, we try to go up until we locate the certain optimal solution or the optimal region. And then from the optimal region here, we will know that what is the optimal solution we have. Okay. So we have a two procedure here, whether you are going the upward or the downwards here. So this one was related to the maximum or the minimization problem. So the method of the signal action is a procedure moving sequentially in the direction of the maximum increase of the response. So if you are looking for the maximum, then you are going for the signal action. Whereas if you are looking for the minimum is desirable, then the technique is called the method of the signal decision. Okay, so our starting point will be the first order models here. So the first order model is this one is if you still remember how you want to estimate beta naught and beta 1, I have mentioned it to you in the previous part 1 lecture notes. Okay. So this one is where the direction of here. Okay, because it's a linear form, so therefore they at this region they try to locate try to increase the steps until they can locate the optimal solution. So this one is called the path of the signal action because they're going up. If you're going to the other direction for the minimum, then it's called the method of the signal decision. Okay. So the technique will be very simple. Then we'll go through the following one. This one is what we have the experiments. Before that, you also will see it before under the ANOVA. Okay, a chemical engineer is interested in the determining the operation condition that maximize the yield of the process. So in this case, we are looking for the maximize of the yield of the process. So the two controllable variables influence the process yield. The first one is a reaction time, and the second one will be reaction temperature. Same like what you have studied before. This one is your first factor, the factor A. This one is you can call as a factor B. Okay. Okay, so you want to study about the two factor will be influence the yield of the process. So the first factor we consider will be the factor A is a reaction time. The second one will be the reaction temperature. So the engineer is currently operating the process with the reaction time of the 35 minutes and the temperature is 155, which resulting the yield around the 40%. Okay, so because it's unlikely that this region contain the optimal, so he should fit the first order model and apply the methods of the signal action. Okay, so they will found that this one is still not the around the only the 40% only. So they think that they may can be find out where is a region where they have an optimal solution. Okay, so this one is what you have familiar with. The first one, this one is what you have here. Okay, so both of them at the low level, we using the notation as a 1. Okay, under the 2 power of 2 factorial design, because you only for the first one is only the 2 level, the second one only the 2 level here, 150 and 160. So we try to convert it to the -1 and the +1 or the 1 here. So this one is both at the low level is a 1. This one is for the second one is a high level. So I use a notation for first one is a A. This one is a B. Okay, so therefore this one will be the B. This one will be the A. Then this one, both of them have the high level is a AB. Okay, this one is what you have familiar with, the notation what we have used before. Okay, and then in your previous parts of the response surface methodology, I also have mentioned to you what is called the center point. So the center point is the middle of these two values here. So the middle of them is a 35. So you have the second one, the factor B, you have a 150 and the 160. So the middle of these two is a 155. If you convert to the coded variable, then the 0 will be the center point of here. Okay, so this one is what you have before that. Okay, so of course we can find the relationship. I have mentioned it to you. X1 you can write as a X1 will equal to the Z1, okay, minus by the 35 divided by the 5. Okay, how to get the 35? Okay, so this one is I have mentioned to you. You just take the average of these two, then you get the 35. You're going to get the 5 here. You get the difference of these two, 40 minus by 30 divided by 2. You get the 5 here. So the X1, if you substitute the Z is the 30, then you get the answer is -1. If you substitute the value is 40 here, then you get the positive 1. If you substitute the 35, then X1 will end out is a 0. So therefore, there are 3 possible values for the X1. X1, they can be the, okay, you can obtain the 3 possible value of the X1. Either the X1 can be -1, 1, or 0. There are 3 possible cases of here. Similarly, if you want to have the coded variable of here, the relationship of the natural variable and the coded variable, the natural variable means that the variable for the default. Okay, so for the default here is this one is in the minutes. This one is the temperature is 150, 160, and 155. Okay, so the second one, if you want to get the relationship of the X2, X2 will be equal to the Z2 minus by, how to get the second one here, you just take the average value of the 160 plus 150 divided 2, you get is a 155 divided by, you want to get the divided by what you have, you just get the difference is 160 minus 150 divided by 2, so you divided by 5 here. Okay, so similarly the X1, the X2 also you will get the value is -1, 1, or 0. You have these 3 value. By substituting the Z is equal to the 150, 160, and 155. If you do not get these 3 value, means that your conversion formula will be wrong. Okay, so after you do the conversion, then should be they will only have is the -1 and the 1 and the 0 only. Okay, so these are the experiment they run. So this point, these are the point is a run for the center point. Okay, because all is a 0, so they run for the center point of here. Okay. So this one is a here. So if we want to have a here is a first order model. If the first order model, then we will put it as a our first order model. We have a y hat will equal to the beta naught hat plus the beta 1 hat the x for the first one plus the beta 2 hat for the x2. If we want to start only the first order model, then we have only the x1 and the x2 is x1 and the x2 here. Okay, the quoted of the x1 and the x2 here. So it's only the main effect. Then of course we need to calculate the beta naught here and the beta 1 here and the beta 2 here. So the beta naught here will be equal to the mean. You substitute, you calculate a value of the average value from all the observation here. Okay, based on the observation here you have, you calculate the average value, then you will get your mean, then plus this one, the beta 1 will be equal to the effect of the first one, or I use the notation as 1, either is 1 or the a divided by 2 multiplied by the x1 plus the second one will be the effect for number 2 divided by 2 multiplied by x2. Okay, so you can be from the previously refer to the part 1 lecture notes, you can calculate the beta, the mean, the beta, the first one, the effects divided by 2 multiplied by x1 and the effects divided by 2 multiplied by the x2. So from here you will get your mean average value will be 40.44 plus the effects over 2 under this case. Okay, so if you want to calculate the effects divided by 2, you just use the plus minus sign of the contrast. Okay, then you can get your value of the effects divided by 2. You get is a 0. Okay, so this one is your initial equation for the following data set. Okay, for the following data set, then this one is the initial equation you have. Okay, so about this one, you of course you can read through the explanation in the textbook where you have a first one x1 and then you have a beta hat of the here. Okay, so the following one is of course we want to find out the optimal solution. But before we go for the optimal solution, we need to check it out. We need to check whether the iteration will be important or no. Okay, so I have here. Before we explore the path of the signal action, the education of the first order model should be investigated. Okay, so how we want to investigate the first order model? Of course, we can be test it out the iteration. Why we don't want to put the iteration? But of course, just now I have mentioned, normally the starting point will be just the first order model. But we still can be do the checking if you plan to use the model with the iteration also possible. Okay, so because as you can see from here under this case will be the 2 power of 2 2 power of 2 factorial design. Okay, without the or you can have a unreplicate 2 power of 2 factorial design. So therefore we need to estimate the sigma. So from here we can estimate the sigma because you have an extra the center point. Okay, so the first thing is you of course you estimate your error. Okay, though that one is a MSE. So how to estimate the sigma? If you still remember it, that one is based on the center point you have. Okay, you have a center point. You calculate the variance of the center point, the first one, to estimate the error. Okay. So this one is one where they use they calculate it using the MSE. Okay, MSE will equal to the sum out of the all the observation. Okay, sum out all the observation of here, the yi minus by the mean square divided by NC minus 1, or the mean of the C here. If you still remember, this one is only sum out for the center point only. You use the observation minus the mean of the center point square divided by NC minus 1, then you can estimate your MSE. This one I have discussed with you when we go through the quadratic effect. Okay, this one is the first thing. The second thing, we can be checked whether the iteration is in the model or no. Okay, so that one I will go through later. I will go through it later. The third one, we can check the quadratic effect. Okay, the third one, we can check the quadratic effect. The first one is estimate the error. The second one, we can check whether the iteration is necessary. The third one, we can check the quadratic effects. Okay, so I have shown it to you the formula before. So the first one is when we calculate the MSE will be given by here. Of course, if you expand the bracket of the square term here, then you can get the following formula. Okay, so it means that all the observation square minus the total square divided by 5 divide NC minus 1. You have all together NC is 5, so therefore they divide 4. So you will get your first one will be your sigma. The first one will be done. Estimate the error. Okay. Then if you want to calculate out the iteration effects also, because this one is a 2 power 2 factorial design. Of course, you can calculate the effects for the iteration effects. Okay, so the effects of them is just a beta 1 1, beta 1 2 is the iteration of the 1 and the 2 here. So this one is just the effects. Okay, you calculate the contrast using the effects. Okay, so how to do it? You can be using this thing. Okay, you have all these things, so you can check it out. This one is a minus 1 is for the 1 here, then the minus 1 is the B, and then this one is a plus 1 plus 1 for the A. This one is both of them AB. So you just use the contrast. Okay, if you still remember, if you base on the factor the AB, the contrast, and then you can calculate out the effect of here. So therefore, this one is what they show it to you. It's 1 multiplied by 39, 1 multiplied by 41, and then for the 40 is minus. In fact, here is just a contrast of here. Okay, the contrast, or they equal to the contrast for the AB divided by n times 2 power of k minus 1. Okay, so this one is what you have for the beta, or the beta of the 1 2 here. Okay. Okay, so you can try it out and then calculate the contrast. Okay. Okay. So after that, you also can be from for the here. This one is this one is just the effect. Okay, this one is just the effect of them. Okay, this one, because the beta 1 2 is just the effects divided by 2. Okay, if you still remember, the effects divided by 2 here. Okay, so therefore the n is equal to 1. The 2 power of k is equal to 2. So 2 power of 2 here, then divided by 2 one more. So therefore this one you get the 4 here. Okay, what I show you to do here is just the effects and then divided by 2 here. Then you can get your beta 1 2 hat. Okay. Then from here, you also can be calculate the sum of square for the iteration in between the factor A and the factor B. So this one will be given by this one will be given by the contrast for the AB square divided by the n times 2 power of k. Okay, of course, in this case, the n will be equal to 1. Okay, because you only have a single replicate, so the n is equal to 1. The k will equal to, because you study is a 2 factor, so the k equal to 2. So by substitute, the n is 1, the 2 power of 2 will be equal to 4. So therefore, you get your sum of square for this iteration here. Okay. Then we can check whether the iteration is necessary or no. Okay, so this one is a carry out the test of the what you have learned before in the ANOVA table, the sum of square for the iteration divided by the MSE. This one will actually equal to the MS for the iteration divided by MS for the error. Okay, the MS for the iteration will be the sum of square for the iteration divided by the degree of freedom is 1 over MSE here is where you have your estimate here will be given by the sigma square. Okay, so this one is what they means by the F there. This one is similar to the ANOVA table where you have this thing, whether you check it out whether it's significant or not. So because this value will be smaller than the F value, therefore this iteration is not necessary in the model. So in your model, you only involve the first order model, okay, where the iteration is not the important. Okay, so this one will be a test for the second one, your iterations in the model. So the iteration of model to show here is not necessary. The third one, you want to check whether the quadratic effect is necessary or no. So therefore, we need to check the sum of square for the pure quadratic. Okay. So how we want to check the sum of square for the pure quadratic here? Then of course we will use the following one. Okay. The formula I have shown it to you before is given by here. Is a sum of square for the pure quadratic will equal to the m for the factorial multiplied by n for the center point, the mean for the factorial minus the mean for the center point square divided by the size for the factorial plus the n for the c here. Okay, so in our case, in the here above the case here, in the above case here, we know that number of factorial point is only 1, 2, 3, 4. Number of center point will be 5. Okay, so you from the number of factorial point, you can calculate the average value of here, and then this part is the average value for the mean for the center point. This part will be the mean for the factorial point. Then the number of factorial point will be equal to the 4. The number of the center point will equal to the 5. So these are the 4 information if you want to calculate the pure quadratic effects here. Okay. So therefore, I can write it out here. The number of the factorial point will equal to 4. The number of center point will equal to the 5. Of course, you need to have based on the factorial point, you can calculate the mean for factorial point will equal to given by here is a 40.425. The mean for the center point will be equal to the 40.46. Okay, so from here you can be check the F statistic here. Of course, you need to calculate the sum of square for the pure quadratic here, will given by this formula. I have shown it to you how this formula is look like. Okay, and then I also have shown it to you how to find the relationship of the mean for the factorial and the mean for the center point. Okay. So this one is the F test here. The F test will be given by the sum of square for pure quadratic is 0.0027 divided by the MSE will be equal to 0.0430. So this one will be you get is a 0.063. Okay. So against under this model here, the quadratic effects here is not necessary because the pure quadratic effect is not significant. Of course, how we want to know the not significant? Of course, we need to have a F test. Okay. We compare it to the F table. Okay, let say consider we say alpha will equal to 0.05. Then of course we will get your f for the alpha here under the f table of the alpha with the degree of freedom for first one is equal to the 1 and the second one will be the degree of freedom. Then you get your f value from the table and then you compare with the f value from the calculation here. So this value is they are quite small here. Okay, so therefore they are not significant. Then you say that it's not no indication of the pure quadratic here. It's not say that we just looking at the value itself. We compare it within the certain alpha level. Okay. So this one will be the following one. This one will be end out for the case where you test that whether the quadratic effect is important or not. Okay, so from here we know that the quadratic effect will be not the important here. So the following one, what we can do under the regression analysis, we can be calculate the standard error for the beta 1 and the beta 2 here. So how we want to calculate the standard error? We can calculate the standard error for the beta 0 and beta 1. So the standard error for the beta 0 and beta 1, we can be given as just the MSE divided by 4 here. Okay, so you just take the square root of the sigma divided by 4. You get your value of the MSE, the standard error for the beta 0 and beta 1 will be equal to 0.1 here. Okay. So under the standard error here, this one I think that we need to relate to the chapter number here. You have here regression model. For this one, we'll be testing the individual values of the here. Okay, the individual of the testing the individual significance of the beta 0, beta j here. So this one is testing the individual. So therefore, as you can see out whether the beta beta j here is equal to 0 or the beta j not equal to 0, then we have a t-test will be the beta j divided by the standard error of here is the MSE multiplied by the x prime x inverse here. Okay, so this one is a testing for the individual. So why the whole thing? This whole thing is actually they will equal to the this one will be equal to the beta j hat divided by this thing is called the standard error of the beta. Okay, this whole thing in fact the meaning is called the standard error. Okay, you use the MSE, then you multiply by CJJ. CJJ actually is the diagonal value of x times x prime x inverse matrix here. So it's actually when you calculate out is equal to 1/4 here. Okay, for our previous just now the case. So this one is why they need the standard error here because they want to test whether they are significant or not. So therefore over here, if you want to know that whether the beta 1 and beta 2 are significant or no, then we calculate the standard error here. Okay. So from the standard error here, we can test the hypothesis for the beta 1 and the beta 2 here. Okay, whether the beta 1 and beta 2 is necessary in the model or not. Okay. So just now you obtain the beta 1 hat. Beta 1 hat, the estimated from the model is equal to 0.775. Okay, or effects divided 2. You have another one is a beta 2 hat will be equal to the 0.325. Okay, so you have these two before that. Okay, from the just now the beginning of the notes of this example. Okay. Okay, so after that, this one is a standard error for each one of them. Their standard error. will be equal to the square root of the MSE divided by 4. Okay, similarly for the standard error for the beta 2 will also equal to the square root of the MSE divided by 4. So this one is the value 0.1. This one also 0.1. Okay, so from here, this one will say that they are relatively large to the standard error. This one is actually, they are mentioned that if you want to testing the beta, 1 is equal to 0, beta 1 not equal to 0. You are testing for the individual hypothesis here. So we are using the t-test will equal to the 0.775 divided by 0.1. So you get is a 7.75. Similarly, you can test the beta 2 is equal to 0 versus okay, so the t value will be here. Then after that, we want to test whether this thing is equal to 0 or not equal to 0. Beside this thing is a test statistic, we also need to set the alpha. Okay, so you can recall back here. If the value here is larger than the t value under the certain alpha, then we have the answer is reject the H naught. So if you reject the H naught, it means that the beta j not equal to 0. Okay. So over here, if we compare with a certain level of the alpha, this value is considered quite large. So therefore, we are the beta not the beta 1 is not equal to 0. The beta 1 is not equal to 0. Of course, you can set your alpha. You can set your alpha is equal to 0. You can set your alpha. Let's say the alpha is the 0.05. Okay, you can set your alpha. Then you look for the t 0.025. Okay, from the t table with their degree of freedom. The degree of freedom for this one, the error here will be equal to the 4 here. Then you look for the t value from the table. Then you compare with this value. So this value will larger than the t value here. So therefore, the beta 1 is not equal to 0. The beta 2 also not equal to 0. This one also, they are larger than that. Okay, so this one is what they mentioned about here. Both are relatively like the error. So we have no reason to question the adequacy of the first order model. So therefore, why our first order model we have only the beta 1 and the beta 2 here. Okay. So now in your in your experiment, before I go through the following paragraph here, what is the explanation of here? Okay, before I go to this one, I will show you the ANOVA table first. So this one is the ANOVA table. Just now we have the first order model. Okay, if you can recall back all the values of the given there. Okay, so we can be test the first order model is the overall model of the beta 1 and beta 2. This one is the sum or square of here. We can recall back the chapter number 10 here. You have testing the individual. You also can testing the overall. This one is testing the overall model. Okay, so you need to calculate out the sum or square for the regression divided by number of the degree of freedom, the number of the k here. Okay, their degree of freedom is k. So this one is a testing for the overall. So this one is similar to here. The model here will refer to the all overall. The sum or square for the overall regression, and then with their degree of freedom is equal to the 2 here. And then after that, you also can calculate the sum or square for total. Sum or square for total is usually what we have used it before. Okay, the sum or square for total is all the observation square minus the grand total square divided by number of observation. Then you can get your sum or square at the total. And then this one is a regression here. And then the total degree of freedom will equal to 8. Why is it 8? Because you have a total degree of freedom, or the total observation you have is a 4 factorial point plus a 5 center point. Altogether is 9 observation minus by 1. Your total degree of freedom is equal to 8. Okay. And then just now I have calculated out the sum of square for the iteration, the sum of square for the pure quadratic, the sum of square for the pure error here. Okay, so all these things is a sum of square here with their degree of freedom for the iteration is equal to 1. The pure quadratic also will equal to 1. The pure error here, you have a 5 observation, then minus by 1, you have degree of freedom 4. Okay, so this whole 1, 4 total out is equal to 6 here. Okay, so here are the tests you can be performed in. Okay, actually just now I do it is separately one by one. Okay, so this one is to show you that the iteration is not significant, because based on the p-value here, you know that they are not significant. Based on the pure quadratic here, also is not significant because the p-value is quite large. But if you're testing the model of here, beta 1 and beta 2 together, not testing the individual, you can see that the p-value will be quite small. Therefore, this model with the beta 1 and beta 2 is adequate. Okay. So we do all these things is want to maintain that, want to make sure that the model, what we starting point of our first order model. Okay. So now we have a model itself. Now we have a model. The model was given by here. Just now I have a model here. The beta naught. Yeah, this one is a model here. Okay. So we have a model here. Then we move towards the direction. Okay. So because the model here, the important thing will be the size of here and the size of here. The size along for the x1, the size along for the x2 here. Okay. So to move it, the points here, okay, we want to start with the point here, the starting of the point here. Therefore, we need this one. Okay, this one is what I mentioned. I hold it just now. Okay. So to move away, the design center, because you're starting from the 0, 0. Okay, the x1 is 0, x2 is 0. Along the path of the signal action, we will move the 0.75 unit in the x direction for every 0.325 units in the x1 direction. So this one is what I have mentioned just now. We based on the equation what we have just now. The equation we have for y hat will equal to the mean for first one is 40.44 plus the 0.775 x1 plus the 0.325 x2. So this one is a moving size of the x1 is 0.775, and then for the x2 will be 0.325. Okay. So this one will explain for this line. The path of the signal action will pass through the point of here, and the slope is given by the 0.325 over 0.775. Okay. So the slope here, they were using the delta 2 over delta 1 here. This one is a slope here. I will explain to you how we want to get the slope of here. So the engineer will decide to use a 5 minutes reaction time as the basic step size. Okay. So you using the relationship of the Xi1 and the X1, we see that 5 minutes reaction time is equivalent to the size of the steps of the delta 1 is equal to 1. So all these things, I will explain it to you later in the following the tables. So the delta 1, the delta x1 will equal to 1. The delta x2 will be equal to this one. So if you observe this value, actually this value is get it from the beta 2 and the beta 1 hat. Okay. So let me explain about this one is from the table here. Okay, so how we want to go for the path of the direction? So first thing, you start with the origin is 0 and the 0 here. Okay, the quoted variable is the 0 and 0, but if you refer to the natural variable, that one is a meter is the 35, the meter is a 155. So how about our step size? What is the changes of the step size here? Okay, so the first one is if you want to looking for the step size here, how we want to get the 0.42 here? Okay, after we know the 0.22, then of course, then we only know what is the size of the 5 here and the 2 here. Okay, so to get the 0.42, just now we are using the ratio of them. This one is actually is given by the delta for the x2 over delta for the x1 will be equal to the beta 2 hat over beta 1 hat here. So therefore, the delta of the size show the changes in the delta for the 2 here. You want to move the delta of the for the x2 will be equal to the beta 2 hat divided by beta 1 hat multiplied by delta for the x1. Okay, so the beta 2 hat here, the beta 2 hat here, just now we have a formula beta 2 hat. This one is a beta 1, this one is a beta 2 hat, it's 0.325. Okay, so therefore you get is a 0. Divided 0.775 delta for the x1. Okay, so if our delta for the s1 we want to go through it is a 5 minutes. Okay, if every one is a 5 minutes here, if the size of the here is a 5 minutes, so the delta for the one here, the delta for the x1 is equal to the one here. Okay, so the delta x1, if we have a one, the one of here, then you have a 0.325 divided by you will have this one is 0.42. Okay, so this one is how they get the answer 0.42 over here. Okay, with the here will be equal to the one here. Okay, and then because your starting is 0, so 0 plus a delta is equal to 1. 0 plus 0.742 will equal to the one here. Okay, so this one is a 1 here. The 1 here they will equivalent to the origin plus a delta. Because the delta is equal to 5, the step size is equal to 5. Just now we have mentioned we're starting here. So it's a 35 plus 5, you get 40. So every time the step size is a 5 unit. Okay, of course you don't want to have a 5 minute unit, you can use a different unit. So the step size for the here 155 here, you can see that the 0.42 is actually is equal to 2 here. So the step size for this thing is equal to 2. So every time you will increase it from the 35 at, and the 155 at the center point, then you increase by the 5 units, you increase by the 2 units. Okay, how to decide the 5 units and 2 units? They were given by this equation, the relationship here. Okay, of course you need to have a fix of the certain level first. You increase for the 5 units here, then you will know what is the xi2 for the second variable here. Okay, so this one is you can see that they increase for the every units, from the origin plus delta, origin plus 2 delta, and so on. So when you run for the here, under this condition of the 40, this one is referred to the first one. In fact, the first one is referred to the reaction time is a 40, and then the second one will be the reaction temperature is 157. So based on this one, you you run the experiment, then you get the answer for the response is equal to 41. Then after that, you move to the second, the next stage will be equal to origin plus a 2 delta here. you run the experiment of the 45 and the 159, then you get your response is equal to 42.9. Okay, so this value is you get from the experiment. Okay, and so on. You repeat the experiment until here maybe is equal to just a 12 delta. So you just increase it. You can see that this is for to obtain the until the certain level, you get your decrease. Okay, so this one is an experiment you run. We cannot estimate this one because we are not running the experiment, but we know the procedure is using the following one. Okay, so this one is a graph you have. So you slowly run the first one at the center point, and then you run the experiment for first one, the second one, and third one. This is the experiment value. You run it out, then they locate the optimal solution here. Okay, so you run your experiment, then you slowly, they will locate until the peak is optimal, then they go down. Okay, so this one will be your optimal solution under the following case. Is called the method of the signal action. Okay, so this one is how to do it is given by the here of this one. Okay, so from the following experiment, you know that if you want to get the locate for the maximum point, then this is the combination you have. Okay, it's the 85 and the 175, you get is 80.3. So of course, if you this because our step size is a 5, so maybe at the level of the 82 is the optimal solution. Therefore, after we get the roughly the optimal solution, then we study in particular about this particular area, whether the quadratic terms will be necessary or not. So therefore, we need to run some more experiments around this region here. Okay, we run the experiment around this region. Okay, because it's a 76 to 80, and then the 76 here. So of course, our region will be concentrated not only here, maybe we are concentrated around this part here. Okay, because we do not know where is a turning point. Okay, of course, here is a turning point because maybe they were at a certain stage, they're higher than here, or after that, they're higher. Okay. So therefore, you have a scoring table. We will concentrate on the 80 and the 90 here. At the 80 and the 90, we run the experiment for the 80 and the 90 here. And then also the 85 here. So this is an experiment we run again. Okay, so the data for the second first order model. So why they suddenly go to 80 and 90? Because from the first diagram here, we will roughly estimate it out. The optimal was somewhere around here. Then we try to locate our optimal is under this region. Okay, under this particular region, we run against the experiment because our ultimate solution is want to get out what is a model is suitable. Okay, so this one will explain to you. If you have here, you can see that you are starting from here, you move it towards the direction of the optimal region, and then under the optimal region, you are trying to find out the model is suitable, whether it's a first order or the second order model. Okay. So they are located for this particular area. We are concentrate on the 80 and 90, and then as well as we run the experiment for the center point. So these are the experiment we run it out. Okay. So after they run out the following experiment here, then they will check it out whether the quadratic terms is a necessary, and then the iteration is necessary. They repeat the same procedure. Okay. So at this stage, at this particular area, of course, they fit the first order model based on the following data. They can calculate the average value. They can calculate the beta 1 head and the beta 2 head. Okay. Then from there, they can check it out whether which one is the quadratic effect is necessary or not. Because this one is a first order model only. Then again, we are checking out whether the iteration is necessary or not, whether the quadratic is necessary or not. This one will given in the following table here. Okay. So from the following table here, we want to check is what is a model we have. If we're testing the iteration is significant at the 10% level. But if you are testing at the 5% level, then the iteration is not necessary because the p-value is 0.0955. Okay, then the second one, we check whether the quadratic terms should be involved in the model or not. So over here, the quadratic term is necessary because the p-value is small. So means that the model will be involve the quadratic effects here. Okay, so from here, if the alpha, we set the alpha, we say the alpha is equal to, let's say, the 0.05, only the 5%, then this one is not necessary because the p-value is larger than alpha. So this one is not necessary. This one is yes here. So we will expect our model, the new model will be have a beta naught hat plus a beta 1 hat for the x1 plus the beta 2 okay, with the quadratic effect. Okay, so in this particular area, under the 80 and the 90 and 85 here, this is a model for us to locate the optimal equation or the optimal solution. Okay, so if you recall back, this one is a beginning of the question. Here is just roughly from the starting point of any experiment. Then they try to go to the optimal solution. Then from this particular optimal solution, they will try to study around this region again. Of course, when we want to study, we need to run more experiment. Okay, they need to run more experiment, then they can get enough data point, and then they run the experiment under this particular region here. Okay, so under this particular region, then they will obtain the following one. This one is the equation what we can consider. Okay, if we say that the alpha is a 5%. Okay, so this one is how you study the method of the signal action and the method of the signal decision. But to apply all these techniques, okay, the idea of the technique is given by here, but you want to work it out, then you need to run the experiment. You need to run the experiment, obtain all the data here. Okay, so therefore, when we go through the tutorial question, our tutorial question, because we do not have a data here, we only will ask you about how the technique is working. Once you know the technique, that just now the delta 2 divided by delta 1 is equal to beta 2 hat divided by beta 1 hat, then you will know that what is your step size to perform it. Then of course, once you know the step size, you run the experiment. You run the experiment, then you can obtain the results. Okay. So this one is about the method of the signal action, and you also can have a method of signal decision. Okay, so just now about the explanation, if you want to looking at the delta, how is it the delta? Is I give you the general steps of here given by the books here. So you're starting of the first order model. Then first thing is choosing the step size in one of the process variable. Just say the delta J. You need to starting with a certain step size. Just now in our previous example, our step size is equal to 5 for the certain variable here. So just now I have a 1 and a 2. So we choose the first one is step size is 5. Okay. So most of the time we choose the variable is those of them is with the know the amount of mass, or we select the variable that have the largest absolute value of the regression coefficient. Okay, because the coefficient can be positive, can be negative. Then one of the option is we choose the largest value as the initial step. Okay, so the step size will be given by just now I have is here is a delta for the xi divided by delta for the xj will equal to the beta for the I hat over beta for the j hat. So therefore, if you multiply it out, you get the following one. This one is just multiply. You get this one or this one. Then you divide by. If you divide, then become multiply. Okay. After that, you convert the delta xi into from the coded variable to the natural variable, so that you know what is your step size you have. Because once you do the coding only can have a negative 1 and a positive 1. Okay. So this is the example just now how they calculate out is get the 0.42. Okay, so from the 0.42, of course, we can convert it to the given the 5 minutes of here. Okay, because the delta for the x1 is equal to delta for the xi1 divided by 5. The delta for x2 will be the delta for the xi2 divided by 5. So from here, they will get the 5 minutes here. And what is the step size is equal to the 2. The temperature is 2 Fahrenheit. Okay. So this one is the first part for the method of the action and method of decision. Okay. So when I give you the tutorial question, you can observe that we only involve the those of the techniques only. We do not run the experiment. Okay. I will give you the tutorial question later. Okay. Then you can observe that we only deal with here. Because if you want to complete the set as given as here, as given as the example here, then we need to run the experiment. Okay, after you locate the optimal solution, then you still need to run the experiment under this part, then you can obtain the following data. Okay, so this one is the first part of the model. The second part of the notes here will be given by the second order. Just now we have seen the first order. Now we go for the second order. Okay. In the second order, when you have a quadratic term is involved in your model, then we can be locate the stationary point, because they can be the maximum, they can be the minimum, or they can be the shader point. Okay. So this one is a quadratic, second order response surface model. When the experimenter is relatively close to the optimal, like just now, previous example, they are really close to optimal. A model that incorporates the curvature is usually required to approximate the response. So in most of the cases, the second order model will be is adequate. But just now, based on the above example here, we also will test it out. The quadratic effect is really important here. However, the iteration is not significant at the 5%, so therefore we do not include it. Okay, we can be include it inside also. Okay, so this one is second order is important. So now we use the fitted model to find the operating set of the optimal set of the operating condition for X and characterize the nature of the response surface. After we do the fitting of the model, we have already all the parameter estimates, and then we want to know whether this equation, okay, the model will lead you to the maximum or the minimum, or you don't have the maximum or minimum, we call it as a shader point. So we want to know what is the operating condition for the X. The operating condition of X that lead you to the what is the optimal solution you have, okay, or the nature of the response surface. So to do so, I just show you for the special case of here first. Okay, consider we have a k is equal to 2, means that we only study the factorial design, and then in this case we have the two levels with the 2 factors. So this one is a full model we have, where the main effect, this one is a main effect, this one is a quadratic term, this one is an iteration effect here. If the full model is here, then the fitted model will be with the head here. All these things you can estimate it out from the model, and then the beta 11 and beta 22, of course we need to run more experiments so that we can estimate it. Okay, so assume that we have already estimated all the beta naught, beta 1, beta 2, and the beta 11, 22, and the 12. We can estimate all the parameter estimate. So end out, this equation will be lead you to the maximum or the minimum solution. Okay, or you have another optimal solution. So this one is here. will write it down for you, the equation. Okay. Or we will write it out in the following one. Okay, so this one is here is an equation here, or we can write out the equation in terms of the following form. Y hat will equal to the beta naught hat still continue. Okay, I will write it, these two terms. Actually, if you multiply for the following, for the this part multiply by here, you get the second one. Okay, these two I will write in this form because later on I will want to generalize in the certain format. Then these two will be go to the here. This one will be here. Okay, then for the this part here, we can be written it as a okay. If you multiply this one with the following matrix and then multiply it again, you end out will get back the same thing here. Okay, we will here where your x1, x2, you multiply with this part and then multiply again, you will get this 3. So this one is over 2 here. I just put it here. Okay, you try to multiply one by one, then you will end out this 3. So this equation we can written as a following one. Okay. So or we can be called this thing is equal to the beta naught hat plus the this one is an x. If the x is I write in the following one, then I call as a x transpose. Okay, this one is a vector. Then multiply by this thing I call as a b. Okay, this whole thing I call as a vector of the b here. This one is a b here. Then plus the following one. Okay, I use here. I can be use the same thing as a x here. Okay, this is a transpose. This whole thing I call it as a b. Okay, it's a matrix of the b here, then multiply by the x. Okay, so this one is what we need to get. Is an important thing. Is a okay. Okay, the important thing will be here. This one. This part here. And then you need to recognize the b is this whole thing. Okay, so if you have a quadratic equation, you only need to recognize this one, the b and the b here. Okay, I will write it down here. I will explain to you the b here will equal to the this thing. Okay, for the beta 1 hat and beta 2 hat, where the capital B will equal to this thing. Okay, so this one is a and B. The B, the small letter B. This one is a capital B. Value of the B here. Okay. So now if you want to look for the here, so now we have a following equation of given by here. If you're looking for the optimal solution for the x here, because you only have an x1, x2, then of course we will deal with the differentiation of the y hat with respect to the x1. Because we want to looking at the what is the operating condition for the x1 and x2 such that this thing is optimal. So the optimal can be the minimum problem, can be the maximum problem, or can be another one is where you get is a shader point here. Okay. So of course, when we do the differentiation of this thing, okay, you differentiate with respect to the x1. If you differentiate with respect to the x1 from the equation here, the beta node will be constant with 0. You treat the x2 is also the 0 here. Then you only have x1, you differentiate, you get the beta 1 hat. Okay, then differentiate with the x1, you get the plus 2 of the beta 1 hat x1. Then for the here, you get the plus the beta 1 2 hat. You have a x2 here. Okay, if you differentiate with respect to x1. If you differentiate with respect to the x2, so we are using the similar idea. Differentiate with respect to x2, you get the beta 2. So you will get your beta 2 hat plus the second term will be differentiate with respect to the x2, you get the here you have this one, and then you have the last one will be here. Okay, so I just copy down it here is equal to the beta 1 2. Okay, you can check it out. This one is the first one is a beta 1. This one is a differential with x2 beta 2. You differentiate this one, you get the 2 beta 1 1 x1 x1. If you differentiate with the x2 here, you should be have not this one. Okay, you will have the 2 beta 2 2 x2 here. Okay, and then for the third one here, you will have the following one is equal to the here you differentiate with the x2, you get is a beta 1 2 x1. Okay, so of course these two can be interchangeable position here. So this one is actually equivalent to the if you do write it down, they actually is equivalent to the okay, if you differentiate it out, okay, you can see that you differentiate x1 and x2, you get the distance out. So they actually were equivalent to the what you have is the beta 1 hat and the beta 2 hat. Okay, you have these two, and then plus the second one will be equal to the you have a x1, x2. Why I arrange it? Because later on we will multiply it. You have a 2 times the beta 1 1 hat, beta 1 2 hat. Okay, so this whole thing is actually we can write it here. If you multiply this one with this one, you get the first one. Okay, it's beta 1 here, 2 times the beta 1 1 x1 plus the beta 1 2 hat now x2, you get the first equation. If you want to get the second equation, it's just the beta 2 hat, and then the second one will be this one times here, that this one times here. This one is the reason why I write the x1 first, followed by x2. Okay, so you will get the following one. So if you observe this thing, you will get your beta 1 hat Okay, we factor out the 2 here. So this one is similar to what you have just now. I have denoted at this one is equal to the B. This one is equal to this one is a B here. This one is a capital B of the metric here. So therefore, this thing is actually equal to the B plus the 2 times the B multiplied by the X here. Okay, this one is if you do it here, you will get the following one. Okay, then of course, we need to differentiate it for the Y hat over differential for the X. We put it as all the point here, it will equal to 0. We call the S for the stationary point will equal to 0. Okay, sorry, no, we substitute with the stationary point here will equal to 0 because we are looking for the equal to 0 or the stationary point here. So if you have here, then you substitute with the SS. The SS is denoted as a stationary point. Then we have a B plus the 2 of the B multiply X for the stationary point will equal to 0. So end out, you get your X for the stationary point will equal to the minus half. Yeah. So this one is the equation you are looking for. Is one to get your stationary point. So you need to know what is your B, what is your the B of the metric, what is here the B here. Okay, so I have mentioned to you that the B will be given by all the beta 1 and beta 2 hat. The capital B here is equal to the coefficient of the quadratic term at the diagonal. The off diagonal will be the iteration terms here. So maybe your iteration term can be possible is 0. But you use the iteration 1 divided by 2 here. Okay, and the iteration of the beta 1, 2 hat divided by 2. So this one is your capital B. Okay, so finally, once you can recognize these two, then we will know that your stationary point will equal to negative 1 or 2. The inverse matrix here multiply B, so you get your stationary point for the X1 and the X2. Okay. So of course, once you get your stationary point, we can know that what is the predicted point. Okay. So this one I call as a stationary. Okay, you have a stationary point is XS will be given by here. So you can be predict. Okay, the predicted of here, because you're going to get the stationary, just now your equation will be equal to the Y hat, will be equal to here. Just now your equation is here, or your equation can be written as this one. Okay, I will write it down here. Your prediction equation will be equal to the beta naught hat plus the X for the stationary transpose multiplied by the B. Okay, you substitute by the stationary point plus the X for the S transpose. Okay, multiply B for the X for the S. Okay, so because your the XS here, you can be substitute with this one. Okay. Okay. This one I think I put the tail for the one. This one's minus, I will put the minus here. This one B times the B inverse is the identity. So therefore, you have a okay. So this one is a 1, this one is half. So therefore, finally, you get your fitted value will be equal to the half of the. Okay, so this one is your final answer of the fitted value. Okay. So this one is what you have. First thing you derive out this equation. Then after that, you are getting the following one will be the what is the fitted equation for the following one is even by here. Okay, so this one is what I want to tell you about the for the case of the 2 by 2. Okay, so in general, you can see that if you have many of the equation, you have a beta, you have a study for the k factors with the different levels, then you can be looking at the optimal, whether it's maximum or minimum. We also using the same idea, differential for the y hat with respect to x1, differential y hat with respect to the x2 until the differential y hat with respect to the xk, then equate to the 0. Okay, so if you equate to 0, of course, we will write in the following form. The form here, it will be equal to the x prime b and the x prime b times the x. So this one just now I have shown it to you. Okay, then you can be write out all the x is given by x1 until xk. The b, the small letter b will be equal to beta 1 hat until the beta k hat. The capital B matrix here is the diagonal will be your quadratic component. The off diagonal will be the iteration divided by 2 for the off diagonal. And then this one is a symmetrical matrix here. So the upper side and the lower side will be symmetrical. Okay, so this one is what you identify the B and the small letter b and the capital value of the B here. Okay. So after you get it out, then you will get your equation of the stationary point. You just find the E, capital B inverse, multiply B here, then you multiply by minus half, then you get your stationary point. Okay, so this one is a general, the special case. This one is a the specific for the general case of here until the K level. Then of course, this now I have shown it to you how to get this equation out, and then the stationary point also I will solve it here. Okay, so we will stop until here first. Then after that, we still not try to locate whether this one is a maximum or the minimum problem yet. Okay, so we stop for the while. Now it's 7:28. Then we stop for a while. We continue at the 8 o'clock. Okay.